curve sketching. I know that probably graphing was not one of your most favorite topics throughout math all the way through, but now we can graph even better by using what we know about calculus. All right, so let's take something that you graphed in the past, this parabola. Y equals 3x squared plus 12x minus 1. So throughout mathematics, we learn different techniques for graphing. The very first technique that you learned was just plug in x, find out y is, plug that point in, right? And if you got enough points, you would get the shape of the graph generally, right? What's the problem with table of values and plugging in points? Well, it gets a little bit of annoying and it can take a long time. So then in grade 11, you started looking at parabolas and you were like, ooh, if you can change this to the vertex form, then you could draw your vertex, and then does this one open up or down? It opens up. We know that because of the positive 3. If you found your vertex, you might remember, oh, I go over 1 up 3, over 1 up 9, over 1 up 15. Maybe you remember the 1, 3, 5, and then multiples of it. Maybe not. But could you change this into vertex form? You would have to, what's the strategy we used? Completing the square, right? So this is grade 11 technique. You factor out that 3, then you say to yourself, what would I need to add to make it a perfect square inside? Now when I add that 4 inside, why do I subtract 12 outside? Because it's multiplied by 3. And back in grade 11, this was quite a complex feat. Does it look bad now? So you find your vertex. Now that we have calculus, the vertex becomes even easier to find. Because what is the slope of the tangent line going to be at the vertex? It's going to be 0 because it's flat. So if we find our derivative and set the derivative equal to 0, look how long it takes us to find the vertexes at -2. Look at the complicated math we have to do. We have to solve 0 equals 6x plus 12. And then once you know that x is -2, you could plug that back into the original equation to find out the value of y. And so this, you look at the math on both sides. They're both not super complicated, but finding the derivative was really quite easy to find that x coordinate and then find the vertex that way. What's going to be nice about calculus is although we have a special way to find the vertex with parabolas, when you graphed cubic functions in grade 12, you always just sort of estimated where the maximum and the minimum was. And now you'll have a nice way to add that into your graph. So, calculus is about slopes of tangents. And these slopes can tell us a lot about the graphs. If f prime of x is 0, which we were talking about before, what does that mean for your graph? The tangent line would have a slope of 0. And that will always mean that your graph either bottoms out with a minimum or has a maximum. If you think about the vertex of a parabola, you can see why that would be. If the derivative, here we can even draw a picture here. If the derivative is greater than 0, that means our slope is positive. Whoops. And if we take a cubic graph, at the green points, we would have a slope of 0. Where would I be able to draw a tangent with a slope that's positive? Is there certain sections you could say for sure? Or is it going to be random, like one point's positive, one point's negative? Certain sections. So if I picked a point here, would that tangent slope be positive or negative? Positive. Right? And if I picked a point here, that slope would be negative. What about in this section over here? Positive again. So I'll draw that in a black dot. And so similarly here, if f prime of x is less than 0, what does that mean? Well, that means that the slopes of the tangent lines would be negative. And so we start to look for patterns within this. What happens when the slopes are positive? What happens to the graph when the slopes are negative? What happens to the graph when the slopes are 0? Well, the zeros are easy to see. They're going to be where you have maximums and minimums. Can you see that on this x cubed graph, everywhere before the first maximum, the slopes are positive? And that everywhere between the maximum and the minimum on that graph, the slopes are negative. And everywhere after that minimum, the slopes are positive again. And so we're going to start describing this as, increasing and decreasing functions. So first of all, we say a graph is increasing if, as you go from left to right, it's rising. So our cubic graph that we drew in the last picture, it was increasing until we got to that first maximum because it was rising from left to right. And then in between the maximum and the minimum, that graph was decreasing because it was going down from left to right. And so we have a very similar x cubed graph here where we can label the maximum and minimum points and show where it's increasing and decreasing, which we've talked about already in the previous graph. So the blue section, I don't know how you want to highlight it in your notes. Maybe you have different colors, or maybe you just label it in a different way. The blue sections are where the graph is increasing, and the red section is where it's decreasing. So we start to get a sense of how calculus may be able to help us graph things. Calculus makes it very easy to find maximums and minimums because you find your derivative and you set it equal to 0 because when the tangent is horizontal or has a slope of 0, you're going to have either a maximum or a minimum. Then you can also use your derivative to find out when is my derivative positive, when is my derivative negative. And you can tell when your graph is supposed to be increasing and when it's supposed to be decreasing. And with those little bits of information, you can draw quite an accurate graph of any function. So any place where it is increasing, will have a positive gradient, the slope will be positive, and anywhere where it's decreasing will have a negative gradient. So we've got a couple of examples here. We want to find out where functions are increasing and where functions are decreasing. So we need to find out where the derivative is positive and where the derivative is negative. Now, when we find the derivative of this first function, it's just 4x plus 1. If we set it equal to 0, we find out that x equals negative 1/4 is where this graph will have either a maximum or a minimum. Of course, you already know this is a parabola that opens up. So because you know that already, you already know it has a minimum. But we're going to see in calculus how the increasing and decreasing function can tell us that right away. So our critical value is when x is equal to negative 1/4. Again, we already know that that's going to be a minimum. But we can draw, the next thing we're going to do is draw a number line. And on that number line, we're going to label negative 1/4. Most likely, what you're going to do after the fact is after you have drawn your number line and labeled negative 1/4, you're going to do a test value less than negative 1/4 and greater than negative 1/4 into your derivative. So what's a value less than negative 1/4? Negative 1, right? Negative 1 would be less. If you plug negative 1 into your derivative, so I'll put a green box around the derivative right here. If I plug negative 1 into that derivative, I would get negative 4 plus 1, which is negative 3. Okay? I've written it underneath here, f prime of x is less than 0, but you could just show it with a negative sign, and then a negative derivative means your graph is decreasing. So I find it really easy to see what's going to happen with your graph if you draw an arrow pointed down to indicate decreasing. So probably afterwards you won't write this f prime of x is less than 0. We'll have it in our notes right now just to explain what's happening. But you're just going to say this section's negative, that means it's decreasing. What happens if I plug in a number bigger than negative 1/4, like 10? Well, 4 times 10 plus 1 would be positive 41. You'd probably put a positive sign here and then draw your arrow going up, because if your derivative is positive, it means that it's increasing. Okay? Why is it always positive after that? Well, we only have one critical point. The derivative is only equal to 0 once. Right? It's an equation of line, y equals 4x plus 1. You can't have it go positive and come back down into negative unless you have another x-intercept. Those x-intercepts are really important because those are the only places your graph changes, your y values change from negative to positive only if they hit an x-intercept. And so we need to find all of our x-intercepts and then just check those sections. Is my graph positive or negative on either side of those sections? Now that we have this, we have enough information to graph. We can say that we know that it's decreasing from negative infinity all the way to negative 1/4 and increasing all the way from negative 1/4 to infinity. So we've stated the intervals where it's increasing and decreasing, and we could draw our graph. If we wanted to find the y-coordinate of that vertex, you could plug in negative 1/4 back into the original equation. Right? And sometimes, I mean, This may seem like common sense, but you might want to put it down. Points on the graph now, it is so common sense because this is true all the way through, right? How do you find a point on a graph? You plug your x value into your original function, okay? But what happens in calculus is sometimes we plug values into the derivative. And later on, sometimes we're going to plug values into the second derivative. And sometimes you plug values into the original equation. And your mind might get confused because you're plugging in things all over the place. So even though you might say right now, this is common sense, sometimes your brain learns something new, and uncommon sense is something that was common sense. Is that a verb, uncommon sensing? Maybe. We just invented it. Okay? So this is common sense right now. Let's keep it common sense. If you want to find a point on your graph, you plug that x value. So we know that the minimum happens at -1/4. We can plug -1/4 back into our original equation to find the y coordinate at that point. The nice thing about your diagram here is that with the arrows, you really can see what the shape of the graph is going to be. It needs to go down and then back up again. When did you do number lines like this in the past? You did number lines similar to this when you did true, false, true back in inequalities of parabolas. That was the first time that you sort of put number lines and put your x-intercepts on there and did true, false, and true. It comes up again now in calculus and is really, really important. Okay, now the parabola wasn't that exciting because we could graph parabolas from before. Graphing this equation, yes, we learned techniques in grade 12 to do this one. But now let's look at what our calculus would say. If we find our derivative and we set our derivative equal to 0, we find out that your tangent slope is equal to 0 at 2 different points. At x equals 2 and x equals -1. Draw your number line, and on that number line, put those critical points. Again, you can have this in your notes underneath now, but probably afterwards you won't write that out. You will just have, this is what I would do. I would have this. Right? This is nice to write in right now just because of the negative signs, but I would just have this, and then I would pick a point less than -1. And you don't even have to do all the mental math. In fact, we're going to use our factored part right here and say if you plug in something less than -1, like -2, you would have 6. -2 minus -2, I know it's -4, but I'm just going to put negative there because it doesn't matter what negative number it is. And when I plug in -2 into -2 plus 1, that's also going to be a negative number. What's a positive number times a negative number times a negative number? Positive. I'll just put a plus sign there, and that means that section's increasing. So mental math-wise, you just have to hold positives and negatives and not have to worry about exact values. Because if that section is positive once, it'll always be positive. if you try a number between -1 and 2? What's a number between -1 and 2 that would probably be the easiest mental math? 0. This will stay 6. 0 minus 2, that section would stay negative. 0 plus 1, that section's positive. 6 times a negative times a positive will be negative. And so that section would be decreasing. And finally, something bigger than 2. Say you plug in 5. 5 minus 2, this is positive. 5 plus 1, that's positive. 6 times a positive times a positive, positive. So using your factored derivative is going to be the easiest to find out where things are positive and negative. Because you could have plugged it into the original equation, but then you might have to do a little bit more math. And it might be a little bit more difficult. However, in this case, right, plugging in 0 into the original one to get -12 would be quite easy. But often the factored one makes it easier. Okay? Now, how would you have graphed this in grade 12? Okay, in grade 12, you would have learned that this is a positive x cubed graph, so that its end behavior acted like a line, or its end behavior was falling to the left and rising to the right. And then you just say, well, there's going to be something in between, but you would know that. You would have factored this to find out your x-intercepts, if possible. And then you would have drawn your sketch as best as possible, but in grade 12, there was no way for us to know exactly where our maximums and minimums were. But now that we've taken the derivative, we can state which areas are increasing and decreasing, and we can draw the graph. And on our graph, we can now label our maximum and our minimum, right? And from our arrow diagram, increasing, decreasing diagram, it's pretty obvious that -1 is going to be your maximum and 2 is going to be your minimum. A little review from grade 12. In grade 12, you would have known the shape of the x cubed graph. You would have factored this by taking out a common factor of x, leaving you with 2x squared minus 3x minus 12. And then you might have spent a bunch of time trying to factor the inside. Unfortunately for the inside, doesn't factor nicely. So then you'd have to use your quadratic formula, and all of a sudden it's starting to sound a little bit messy, right? The fact that I factored out 1x means that I know that I'm going to have the point 0, 0. But my other x-intercepts would have been difficult to find because I would have had to use the quadratic formula. But if you did use the quadratic formula on 2x squared minus 3x minus 12, you would have found these other points as well. And in grade 12, you would say, I know that it starts down here and has to end up here. You would just go through these points and estimate where the maximum and the minimum were. But you didn't have to find them exactly. But now that we have calculus, we get those points quickly as well. So we can use that plus what we know about how to find x-intercepts to get a really accurate graph of what's going on. Here's another one you would have graphed in grade 12. A positive x to the 4 graph. So you would know that its end behavior acted something like a parabola. And because it has a positive leading coefficient, it would open up. But you didn't know what was happening in the middle here. It might have a W, it might have some other interesting stuff. That part you weren't sure of. Now, when we go to calculus, we can find the derivative of this, set it equal to 0. It factors really nicely. And we get 3 critical points. So what I'd like you to do is next draw the number line and label your critical points and plug in values to find out where is it increasing, where is it decreasing. You ready to see? Check how you did. Again, I would probably label here, plug in something less than -2. This part would be negative. This part would be negative. This part would be negative. A negative times a negative times a negative would make that section negative. Plugging something in between, there, let's just clean this up a little bit there. Plugging something in between -2 and 0, -1. This would still be negative. -1 minus 2 is still negative. -1 plus 2, this one's now positive. A negative times a positive will be positive. Okay? Between 0 and 2, choose 1. This will be positive. 1 minus 2, still negative. 1 plus 2, positive. That section will be negative. And finally, if you plug in something bigger than 2, all 3 of those sections will be positive. And so we can see that it's going to go down, then up, then down, then up. We can label the intervals where it's increasing and where it's decreasing. In interval notation, when you have 2 different sections that are increasing, you write both intervals separately and then you put a U to show or. It could be in this section or this section. Plugging in -2, 0, and 2 into your original equation will give you the exact points where there's maximums and minimums. On that graph, the red section shows that it's decreasing from left to right, and the blue sections show that it's increasing from left to right. This one in particular, using the techniques you would have learned in grade 12, would not have given you a very accurate graph at all. The only thing you would have known from grade 12 is that it started up here and ended up here. You might have been able, through a little bit of creativity, to find your 2 x-intercepts and your 1 y-intercept. But you wouldn't have known, does it just go through it like that? That could be a possibility. Would it go down and up like this? You wouldn't know exactly where those things were happening using grade 12. Grade 12, you would just been able to say, I know where it ends, and I know where my x-intercept and y-intercept are. Other than that, I'm guessing. And so in grade 12, if you wanted to guess more accurately, you had to go way back to the very first technique for graphing that you knew, which was table of values. And just plug in a bunch of values for x and find your values for y, which after putting a couple to the power of 4, you would get annoyed with, oh, the mental math is so annoying. I don't want to graph this anymore. But now, with increasing and decreasing and the key points of maximums and minimums, we get a very accurate graph of what's happening. So we're going to take some of the knowledge that we learned from grade 12, like finding x-intercepts and y-intercepts, and now that we have our maximums and minimums, we're going to be able to draw much more accurate graphs. Let's look at some other graphs you did in grade 12. Remember ones like this. Rational equations and graphing them. These ones had a whole bunch of different kinds of asymptotes. Sometimes they had holes in the graph. How do we find all of that out? Well, let's start with our calculus. We would have to use our quotient rule for derivatives to find our derivative. So keep the bottom the same, derivative of the top, minus keep the top the same, derivative of the bottom, over the bottom squared. Now that you have your derivative, we're going to simplify this. And then, if we're going to set our derivative equal to 0, one thing about solving for when a fraction is equal to 0, okay, it simplifies very nicely to be 6x over x squared minus 1. And the only place that a fraction is equal to 0 is if your numerator is equal to 0. Technically, if you wanted to, you could multiply both sides of that equation by the denominator, and your denominator would just go away. But if you think about it, if a fraction is equal to 0, the numerator has to equal 0. And as long as your solution isn't one of the non-permissible values, right, x can't equal plus or minus 1, because then you would be dividing by 0, then our only critical point is when x is equal to 0. So now we can draw our number line. We can find out where things are positive or negative, but we also add to our number line the non-permissible values. So a little note that we can put under here, our critical points that we put on that number line include non-permissible values and where our derivative is equal to 0. Going back to grade 12, because sometimes we're going to use the new things that we learned about calculus and the things that we learned from previous years to help us graph this. What did those non-permissible values do to your graph? Okay, they either made holes or asymptotes, right? what will they do in this situation? These ones will be asymptotes. Do you remember when you had holes? Right? If one of the non-permissible values canceled out with a factor in the top and it went away, that's when your graph had a hole. But in this case, the x plus 1 and the x minus 1 don't factor and go away. Then they stay as asymptotes. Are they vertical asymptotes or horizontal asymptotes? Up and down or across? Up and down. They're vertical. Do you remember how you found out if this had a horizontal asymptote? It's okay to say no. Okay, so horizontal asymptotes talk about what happens to the graph when x gets really, really big. Either big positive numbers, that's for use this direction, and big negative numbers this direction. Okay? So as x gets really, really big, what you might have learned last year is you can just look at the highest degree, so the x squared and the x squared. And if I think about x being really, really big, right? A billion squared, if you had $1 billion squared and you lost $4, would it make a difference? No. So the other numbers really don't make a difference. And so if you ignore everything except for the x squared and the x squared, this one has a horizontal asymptote at y equals 1. Because x squared over x squared is going to get really, really close to 1. The bigger the value of x gets, right? A billion squared divided by a billion squared is going to be really close to 1. And subtracting that 4 and subtracting that 1 won't make a big difference. So when we go to graph this, we draw our asymptotes in. We now know that we're going to have a minimum at 0, 4, because if it's decreasing and then increasing, you can see at 0 you're going to have a minimum. And with your asymptotes drawn in, you can say the only way I can be decreasing in this section with these asymptotes is if I start here and go down. And the only way I can be increasing in the last section is if I start at my asymptote and go up. I found my minimum to be at 0, 4. You could use what you know about X-intercepts. To find your X-intercepts at 2, 0 and negative 2, 0. And so this one did involve still a lot of stuff that you knew from the past, right? We needed to use how we found asymptotes in the past for this graph. The X-intercepts, right? How do you find an X-intercept? You make y equal to 0. And if I make y equal to 0, the only place that a fraction is equal to 0 is if your numerator is equal to 0. I can factor my numerator. I could factor my denominator as well. And by doing that, I notice that I'm going to have X-intercepts at 2 and at negative 2. That, and using the fact that we know where it's increasing and where it's decreasing, we can draw a very accurate graph once again. Yes, I can scroll up. So in grade 12, to review how you graph this in grade 12 you would have found all of your asymptotes. first. You would have then found x-intercepts and y-intercepts, and you would have had those two green points and that black point labeled. From that, you would have just then said, I can draw it towards the asymptotes and be done. So you would have said, I know that the graph has to go this way because of my asymptotes in both sections. And at 0, 4, you would say, I know it has to go up towards my asymptotes because if it went down, I would get 2 new x-intercepts. And I've already found all the x-intercepts that there are. So in this case, in this example, I'm not sure that the calculus has really added a lot to our graph that we didn't know from grade 12. The only thing that it verifies is that 0, 4 is the smallest it ever gets in that section. In grade 12, you would have probably just estimated that 0, 4 was the smallest, but wouldn't have been able to say for sure that 0, 4 was a minimum in that section. All right, one more for you to try. Found your derivative, set your derivative equal to 0 and got 0. Drew your number line, and your number line after plugging things in, because it's 6x squared, it's always positive. And so it is always increasing. It is never decreasing. But at 0, it flattens out. So if we look at our graph, which is 2x squared minus 5, when I drew my x cubed graph, you sort of realize that I should have flattened it out even more. Because technically, what happens right at the key point on your x cubed graph is you have a tangent that's 0. This is one of the few cases where you draw a tangent line and it actually cuts through the graph. Usually a tangent line touches the point only once but doesn't cut through the graph at that point. But on an x cubed graph, it does. And if you plug 0 into the equation, well, you get 0, negative 5. But you can see from the graph that we have our vertical stretch by a factor of 2 and a translation 5 units down. So our techniques from grade 12 are probably quickest in this example for graphing it. Now we have one more example to do. All of the examples we've done so far have been nice polynomials. So it'd be good to look at an e to the x graph. I made some changes. So y-intercept is at 0, 7. Part of the graph is shown on the graph right here. Part A, show that a is equal to 5. Well, how do we show that a is equal to 5? We know the equation. We know that it goes through 0, 7. Can label that point on my graph. What does that mean? That means when I plug in 0 for x, y has to be 7. It doesn't matter what k is, because k times 0 would be 0. And solving for a, you get a is equal to 5. And now that you know a, it says given that f of 10 is equal to 2.67, so what does that mean? That means we have the point when x is 10, y is approximately 2.67. So now that we figured out the value of a, we can plug things in. And we need to solve for k. So a little bit of review of logarithms. If you wanted to solve this one algebraically, okay, you need to get we got e to the k by itself. You're solving for something in an exponent. How do you solve for something in exponent? You take the natural log of both sides, use your log laws, and simplify. Okay? Would you need a calculator for that? Yes. Since you need a calculator for that, you always have to ask yourself, at this point, if I'm going to use my calculator, would it be quicker to put this into y1 and this into y2? Graph them both and find out where they intersect. Would that be faster for me than doing all that algebra? If it is, you should do that on a test. Save time for later. If you wanted to do it algebraically, that's how we would go about it. But if you wanted to find it quickly with a calculator, you could do that as well. Part C, using your value of k, find f prime of x. So you plug in your value of k and find the derivative. What's the derivative of an e to the x? It stays the same. But this one has a chain rule. So the e to the x stayed the same, but then you'd have to multiply by negative 0.201. Hence, explain why f is a decreasing function. Now, the word hence in IB says your explanation has to use what came right before it. So you would receive no marks by saying, I looked at the graph and the graph is decreasing, so it's easy to see that f has to be decreasing. That would give you 0 marks. They need you to use the derivative to explain that it's decreasing. Okay? So, the value of the derivative is always negative. How do you know this? Well, you have a negative number out in front, negative 1.005. What does an e to the x graph look like? Right? It's an exponential graph. That's an e to the x graph. Even if there's a negative inside, that negative would just flip it over the y-axis. There's an asymptote on your e to the x graph at 0. So this kind of question is asking, do you understand how exponential functions work and what their domain and range is? So e to the x, or e to the negative x, is always positive. And a positive number times a negative number will always be negative. And since the first derivative is also always negative, then your function will always be decreasing. Finally, it says write down the equation of the horizontal asymptote. How do we find the horizontal asymptote? That will not use the information here. It's not a hence question. Write down means you just have to write the answer. And once you write the answer, you would get full marks for that. So if we look at our original equation, okay, this is again where you would use transformations from grade 12. It's an e to the x graph. An e to the x graph, which we drew right here, has an asymptote at y equals 0. What does it have at the end? It has a plus 2. What is that plus 2? A translation 2 units up. So that asymptote that was at y equals 0 gets translated 2 units up to be at y equals 2.